Okay, so in this video we'll be doing another exercise about languages and language operations. So in particular, in this exercise we have two languages, L1, which is a power n, where n is any natural number. And for the sake of this video, we're going to assume that n starts at 1. And we have the language L2, which is very similar to L1, except that it's b power n. Okay? And we're asked to compute each of these language operations. Okay, so let's do this one by one. If we do L1 concatenate L2, a very tempting thing to write down will be something like, oh, well, L1 is AN and L2 is BN. So this is going to be AN, BN, where N is a natural number. Okay, so this is a very common error that people do, where they don't really think about the language operation too much, and they just say, well, it's more or less some symbolic manipulation, so it's A and B N. Okay, so I'm going to show you why this is not the case. So if we actually expand this, right? So what is L1? Oops, let's do this in black. So if L1 is A square, A cubed, and so on. And L2 is B squared, B cubed, and so on. Well, what is the uh, output of L1 concatenate L2 when these are your inputs? You have to take every single string in L1 and concatenate it with every single string in L2. So in particular, you take A and you concatenate it with B squared, B cubed, and so on, right? So you get um, all strings that look like A, B power n, right? So you get all of those strings. Wait, let me write it like this. A, B power n, right? Then you do the same thing for a square. So you get a square, and you concatenate this with B squared, B cubed, and so on. So you get all the strings that look like a square, B uh, power something, right? So here, this n, I'm just using it as like a placeholder to mean that it could be any natural number, right? So here, using as a placeholder, just not to confuse anyone. And then so on, right? So I'm going to do the same thing for a cube and for any sort of sequence of A's. So that means that if I put this all together in a set, right, then I'm just going to get all the strings that look like some number of A's and then some number of B's, right? Because some number of A's, some number of B's, if it's any of, if I have A n, B m, whatever n and m are, I can sort of trace them back. I can trace A n back to one of the strings in here, and I can trace this guy back to one of the strings here. And then in the language operation, they're getting concatenated, right? So of course they have to be in here. So what that tells me is that actually instead of being AN, BN, where this would force the number of A's to be exactly the same as the number of B's, it's a lot freer, right? So we have AN, BM, where N is in the naturals. Okay, so that's the first result or the first sub-question. Now, what about the second sub-question? That's when we have L1 square and we're concatenating that with L2 square. So L1 square concatenated with L2 square. Whoops, 2 square. So again, someone might be tempted to write, okay, well, I'm squaring the strings in L1 and I'm squaring the strings in L2. So then I'm probably going to get something like A to N and then B to N. But then based on the logic that we just went through, I think it's clear that it's not going to be that. Okay. But then someone might also say, okay, well, it's not going to be that, but I'm still squaring all the strings. So all of the strings in here are going to be even length, and then all of the strings in here are going to be even length. So then actually it's probably going to be something like A to N, B to N, okay, where N and M are naturals. Okay. But what we're going to see now is that that's not the case. Okay, so let's see what actually happens when you expand the operation. First, let's actually see what L1 square returns. So L1 square, that's taking sequences of A's, putting them in a set, and then concatenating them again with that same sequence of A's. So let's see, what do we get? We get, A concatenated with A square, A cube, and so on. So we get any sort of sequence of A's that has length at least two in that case, right? Here it's going to have length, let's see, at least three. Here it's going to have length at least four, and so on. So it looks like what I'm just doing is I'm creating a language which contains sequences of A's, but there's just a lower bound on how long that string is going to be. And namely, that lower bound is going to be 2 here, because these are the two shortest strings in L1. Well, I mean, this is the shortest string in L1, and it's just reduplicated. So, of course, so the shortest string in L1 square is going to come from the shortest strings from each of the individual languages when you're concatenating them together. Okay, so that was very wordy, but basically what I'm saying is I'm getting like strings, like a square, a cube, and so on, but I'm never getting something like a power one, right? Because there's no way for me to recreate a power one here because I'm always concatenating strings of length at least one together. So that means that I'm going to get, as a result, the language AN where N is at least two. Okay. And I mean, it's going to be the same exact logic for the language L2. So I'm just going to write it quickly here as it's Bn where n is greater than or equal to 2. And now what happens when I actually concatenate these two guys together? So I'm going to get A2, A3, and so on, concatenated with B2, B3, and so on. And so by the same logic, essentially, I'm going to get in my resulting language any string that looks like ANBM, but now there's going to be lower bounds on N, namely it's going to be 2, and on M, namely it's also going to be 2. So that means that I'll get ANBM where n and m are greater or equal to 2. I'm not specifying the fact that they're integers because they must be integers. We haven't defined what a string to the power of 1.5 would be. Okay, and then last but not least, what is L1 star concat L2 star? I'm going to need an extra page. Okay, doesn't want to give it to me. Okay, so L1 star concat L2 star. In this case, I'm just going to skip to the chase and say, well, what is L1 star going to be, first of all? So L1 star is going to be L1 power 0, union L1 power 1, union L1 power 2, and so on. And so you'll notice that L1 power 2, that had a string that looked like AN, where N was at least 2. It's going to be the same thing for L1 power 3, so that's going to be of length at least 3, and so on. Here, they're of length at least 1. And here we have a special string. We have a special language. It's the language that just contains the empty string. Right. So really, because it looks like all of these languages are actually subsets of this language, what we really get is we get L1 power 0 union L1 power 1. And then this is just going to be AN where n is greater or equal to 0. Okay, and then the same thing can be said about L2 star. So that's going to be Bn where n is greater or equal to 0. And so then if we concatenate these guys together, L1 star concat L2 star, then I'm going to skip the logic because I've done it twice already, but I'm going to get something like ANBM. And now, instead of having the restriction that n and m have to be greater or equal to 1 or greater or equal to 2 and so on, they can just be greater or equal to 0, essentially. Right? Because each of these guys contains the empty string. So I can do like the empty string and then any number of b's, including 0. And then vice versa, I can take any number of a's and concatenate it with any number of b's, including 0. And so this is the result of this final language operation for this exercise.